Today we're discussing section 5.6 on applications and models of different growth and decay and also compound interest formulas. So here are objectives for today. All of it is going to come down to this equation, P of t equals P0 e to the RT. I think of this as the PERT equation. That's usually how I remember it, since it goes P0 e to the RT. I can always just refer to it as our PERT equation. Kind of helps you remember it. So in this equation, it always describes population growth. Now, population can be understood in a few different ways, but really, P of t is going to be our population after a given time t. P sub 0 is always going to be our population at time 0. So you're going to see this notation a lot where that P0 shows up right in our equation. And you have to get used to treating this whole notation as one number. So don't let the sub-zero throw you off. It's just one number. And it's always our initial population or initial account value, initial whatever we're talking about. There's going to be a lot of different applications here. So T is the amount of time then that has passed. And R is going to be our growth rate. It's often given in a percentage. So something like 75%. Which you want to enter as 0.75. So you always want to convert your percentages to decimals. Just take your decimal place and move it 2 spots. All right. So note that also our growth rate units must be the same as the actual time units. So you want your growth rate to be something like population per year. Then the amount of time that passes is going to be by year as well. So any population growth graph that we're looking at is going to look like this. It's going to cross the y-axis at our P0 value, and then it shoots off up to positive infinity very quickly. So that in general is what our graph is going to look like. And you'll see a few different versions of this. This one is our positive growth going up to positive infinity. Now let's see our first example. And we have our PERT equation up in the right-hand corner. And so we're going to apply that to this problem. The problem says in 2014, the population of Ghana was about 25.8 million. The exponential growth rate was about 2.19% per year. Find the exponential growth function, estimate the population in 2018, and then at this growth rate, when will the population be 40 million? And for part C this time, we're not going to be using our calculator. We're going to solve it by hand. So let's jump in with part A, find the exponential growth function. So this is going to come from our PERT equation, which we see up in the top right-hand corner. And we're going to want to note P0 is our starting value. Well, our starting year is 2014. And so our starting value that's given is 25.8 million. Now we're told that the exponential growth rate, that's our R value, is 2.19%. That's 0.0219. So to write down the function, we get P of t equals 25.8 e to the 0.0219 t. Now this still needs to be a function of t, so I still want to be able to see my t value there. And we have our initial value and our rate plugged in. Now to estimate the population in 2018, we're really finding P of 2018. Well, that's going to be 25. Oops, you know what? It's not P of 2018. It's P of 4. See, 2018 is 4 years since 2014. So we're looking at 25.8 e to the 0.0219 times 4. And we'll put that in our calculator and see what we get. So we'll switch to our calculator now. And we have 25.8 times e, times e to the 0.0219 times 4. Now, if you don't have a TI-84, if you actually have a TI-83, make sure you put what's up there in the exponent in parentheses. I hit enter and I get 28.162. Back to the slides. We get 28.162, and that's million. And that's it. We just had to plug it in at that point. And again, we didn't want to plug in 2018. We wanted to plug in 4. 2018 would have given us far too large of a number here. Now for part C, we're asked to find when the population will be 40 million. And we have that equation from part A written down already. So basically, when will the population be 40 million? Well, what we got to do is figure out, when does this equation equal 40? Now we have a big long equation, and we're going to solve for our time t. So let's use as much standard algebra as we can. We're going to divide the 25.8 over. And we get 40 over 25.8. We'll save that in our calculator for later. That's e to the 0.0219t. Now at this point, our variable we're trying to solve for is up in an exponent. So we have to take the natural log of both sides in order to be able to move that exponent out of, in order to move t out of that exponent. So we take the natural log of both sides. And I kind of just squeeze it in there when I write this down. And of course, the natural log and e cancel each other out. So I have natural log of 40 over 25.8 equals 0.0219t. Well, now we're just one step away. All we got to do is divide that 0.0219 to the left-hand side. So we get that t equals ln 40 over 25.8 divided by 0.0219. Now that's something we can plug in our calculator, so let's head on over there. And we have natural log 40 divided by 25.8. Close your parentheses and now divide by the 0.0219. We get 20.023. So back to the slides, we got 20.023 as our t value. Well, how does that actually translate back? That means that from 2014, we add 20 years. So 2034, the population will be 40 million. Right? We want to give the answer in terms of an actual year here. And that's the year that the population will be 40 million. And it takes 20.023 years. Now let's see a different example. So that last one was directly population growth. Now we'll see a different example of the same exponential function, but we're not talking about population here. So we're going to say we have a baseball card that sold for $244 in 1980. And it was sold again in 1988 for $410. And we're going to assume that the growth in the value V of the collector's item is exponential. So that tells us we need to be using an exponential function like our PERT equation. So we're first going to start by finding our R value for the exponential growth rate. Then we're going to look at actually writing down the function where t gives the number of years since 1980. Then we're going to think about how long does it take to fully double the value of the card. And we're going to round to the nearest tenth of a year. So let's start with that first one, because we're not directly given a growth rate here. We just know it's exponential, and we know our starting point and then what happened 8 years later. So let's fill in some of that information. We're saying our starting point is 1980. That means that our P0 is 244. So now our equation P of t becomes 244 e to the RT. So we have one variable figured out. We need to figure out our growth rate. That's what part A is asking us to start with. We aren't given the rate, but we are given another piece of information. We're told in 1988 it's $410. Well, that means that 410 must equal 244 e to the r times 8, since 1988 is 8 years since 1980. Well, that's an equation that has all numbers except for our r value. So we can actually solve for r in this line and we'll have our growth rate. So we have used the other piece of information that they gave us to actually solve for that rate. So let's do the algebra here. We got to divide both sides by 244. We get 410 over 244 equals e to the 8r. Now, of course, we take the natural log of both sides. We get natural log of 410 over 244 equals natural log of e to the 8r, which of course is just 8r. That natural log and e cancel each other out. So now we just need to divide by 8. I'm looking at ln 410 over 244 divided by 8, and that's what equals r. So let's throw that in our calculator, see what we get for our r value. We have natural log of 410 divided by 244. Close your parentheses here, then divide by 8. We get 0.06487. Back to the slides. R equals 0.06487. So we found our growth rate. That is the same thing also as about 6.487%, but the decimal will be more useful for part B. So we have that R value from part A. Now let's actually write down the function. We also figured out that our P0 is 244. So therefore, P of t is going to be 244 e to the r, which is 0.06487 t. And that's it. That is our exponential growth function in terms of t, where t is the number of years since 1980. Now let's look at part C. What is the doubling time for the value of the card? You know, how long is it going to take to actually double from 244 to 244 times 2, which is 488. So let's see. We have 488 equals 244 e to the 0.06487t. Again, this is an equation where t is my only variable, so I'll be able to solve for it immediately. So we do 488 divided by 244, which of course is just 2, but we'll leave it like that for now. And that's e to the 0.06487t. Now I take the natural log of both sides, and I get natural log 488 over 244 equals 0.06487t. Remember, natural log of e cancel each other out when we're left with just the exponent. So now I just need to divide the 0.06 over to the left-hand side, and I get ln 488 over 244 divided by 0.06487, and that equals t. So let's go ahead and get that decimal from our calculator. We have natural log 488 divided by 244 divided by 0.06487. 10.685. And it said round to the nearest tenth, so that's 10.7. So that equals 10.7 years, which of course is going to be 1990. Right, we take 1980, we add 10.7, I guess it'd be 1990.7, but that doesn't make a ton of sense as a year, so we'll call it 1990. And that is when the value of the card will actually double. All right, now we're going to see a different problem type. We're asked approximately the same thing, but we're actually not given an initial population. So here the question goes, the population of the Philippines is now doubling every 37.7 years. What is the exponential growth rate? So we're not told the P0 here, notice, but it's actually not going to matter too much. What we know is that after 37 years, we have 2 times P0 as our population, which means I could fill this out as, well, twice our initial population, whatever it was, is the population of the Philippines. And that's going to be P0 times e to the r 37.7. It took 37.7 years to get twice our initial population. And so when we fill out these components, we still have a P0 in our equation, but we also see that we have an R value that we can solve for. See, as soon as I divide the right-hand side by P0 to get rid of it, it cancels on the left-hand side. So I'm left with 2 equals e to the 37.7 r. So notice it didn't matter what the initial population was because it immediately cancels away and we get 2 equals e to the 37.7 r. So to get r alone, we got to take the natural log of both sides. We get ln of 2 equals 37.7 r. And so I can just divide that 37.7 over, and I get ln of 2 over 37.7 equals r. And of course, we can't do that in our heads, so we jump to the calculator and we figure out what is ln of 2 divided by 37.7, and that's 0.0184. So r is 0.0184, or of course 1.84%. But typically we like to have the decimal instead. But notice we still were able to find the growth rate. We found our growth rate r, and we didn't need that initial population. Well, it turns out that that's true in general. There's this nice relationship between our growth rate r and our doubling time t. In general, r times t equals the natural log of 2. So if we solve for r in that equation, we get ln of 2 over t. Or if we solve for t in that equation, we get ln of 2 over r. So when you're given the doubling time, you can immediately use this equation and get your rate. And that's exactly what came out of our work in the previous slide. So the relationship between our growth rate r and our doubling time t does not depend on that initial population. And we saw that in that previous example. The initial population immediately canceled away. So if we tried that problem again, but now we have that equation, it becomes really simple. So if we know that the population of the Philippines doubles every 37.7 years, that's our t value. T equals 37.7. So we immediately jump to r being the natural log of 2 over 37.7, which is exactly where our work led us last time, but now we can just rely on this equation here. It's a nice little formula. And we'll still get 0.0184 here. So immediately we get to our r value. It's quite useful. So keep these different equations in mind. Most often you're solving for the r value in the middle. So now let's see a different application of our PERT equation. See, when interest is paid on interest, we call it compound interest. It's a really nice thing in your bank account if you get to collect interest on interest that the bank has already given you. So suppose that some initial amount, P0, is invested in a savings account with interest rate R, and it's compounded continuously. So interest is always being paid on that interest. Well, then our PERT equation actually gives the amount in the account after t years. So we get our P of t equals P0 e to the RT again. And again, P0 is the initial amount of money. Our P of t gives the balance after t years. So we plug in some time and we get the balance of that account. T, of course, is in years, and R is the interest rate that we're compounding at. So let's suppose we have $2,000 invested at an interest rate R. So it's not given to us. We'll be able to solve for it. We do know that the account grows to 2504 after 5 years. So we're going to find the interest rate. We're going to find the exponential growth function. And then we're going to find the balance after 10 years. And then think about how long until the account has doubled. So what is the interest rate? Well, here we have to solve for it. There's not going to be any nice equation that we can get out of this. It's very particular to these numbers. So we know our P0 is 2,000, right? That's our initial amount. So we always want to grab that first. Then we also know after 5 years, so at t equals 5, P of t equals 2504.65. Really, that's P of 5 since we're plugging in 5 years. Now we know 25, let me give myself a little more room, 2504.65 equals 2,000 e to the r, that's our unknown, times 5 for 5 years. So we plug in the bits of information we know. We know the left-hand side, we know 5 for t, and then we know our initial population, 2,000. Now we have an equation where our only variable is r. We'll be able to solve for it. So let's divide that 2,000 over to the left-hand side. We get 2504.65 divided by 2,000 equals e to the 5r. Now, of course, take the natural log of both sides. We get natural log 2504.65 over 2,000 equals 5r. Again, natural log of e cancels out, and we just get the exponent 5r. Now we're one step away. We divide by 5, and we get ln 2504.65 divided by 2,000 over 5. That's our r value, and we'll turn to the calculator to solve for this. Calculator, we had natural log 2504.65 divided by 2,000. Close your parentheses, then we divide by 5, and we get 0.045. Alrighty, that is our growth rate, 0.045. Our interest rate R, perfect. Now on to part B, we actually want to write down the growth function. So our P of t must be 2,000 e to the 0.045, which we got in part A, times t. We just fill them in to actually write down what the function is. Perfect. Well, now we can use that function that we just wrote down, and we're going to find the balance after 10 years. Well, that's just P of 10. Since our t is in years, right? P of 10, that's 2,000 e to the 0.045 times 10. And let's see what that equals. So that is 2,000, not 5, 2,000 e to the 0.045 times 10. 3,136.62. Okay. 3,136.62. Let me check if I have that right. Yes, 3,136.62. So after 10 years, our account has grown from 2,000 to over 3,000. Pretty nice interest, if you ask me. All right, well, how long does it take for the account to fully double? So remember that we are given those nice equations. We know r times t for a doubling time is ln of 2. So if we're given our rate and we want to find the doubling time, we know t equals ln of 2 over 0.045. And this just keeps it simple. It keeps us using the information that we already know ahead of time. And so we'll jump to our calculator and see what this is. ln of 2, close parentheses, divided by 0.045, 15.4. It's going to take 15.4 years for the account to double. right, on to the next one. So we also may have some population models that actually are limited in their growth. And we'll see an example of this as well. So problems where they're actually going to be limited, so there's going to be a limiting value, are going to look like this. P of t equals a over 1 plus b e to the rt. And a is going to be a number, and b is going to be some number. These are what we call logistic functions, and you'll see exactly what they look like. We end up with a horizontal asymptote at our value y equals a. So let's do an example with this kind of equation. In a town whose population is 2,800, a disease creates an epidemic. The number of people n infected t days after the disease has been given by this function. We have 2,800 divided by 1 plus 22 e to the negative 0.6 t. So we're asked to find a few different things. How many are initially infected at t equals 0? And then find the number of infected after 2 days, 5 days, 12 days, and 16 days. And then using this model, can we say whether all 2,800 people will ever be infected? All right, so how many are initially infected with the disease t equals 0? Well, I'm not sure. Let's plug in 0 here and see what we get. 2,800 over 1 plus 22 e to the negative 0.6 times 0, which of course that's 2,800 over 1 plus 22. Since e to the 0 is 1, we're looking at 1 plus 22, which is 23. So 2,800 divided by 23. No, I cannot do that on my head, so let's go to the calculator. 2,800 divided by 23. 121.7. So about 122 people. Oops. 122 people are initially infected with the disease. All right. Well, now, how many people are going to be infected after 2 days, 5 days, 12 days, and 16 days? And of course, I don't want to write down all of these and try to solve them by hand. So let's do this conveniently with our calculator. See, we're going to go to y equals, and we're going to plot 2,800 divided by 1 plus 22 e to the 0.6. Oh, I think it was negative 0.6. Was it positive or negative? It was negative 0.6 to the negative 0.06. Sorry, 0.6 x. And we close parentheses. And we could look at the graph. We'd have to try to figure out what window we want to see. So instead, we're going to look at the table, and we're going to scroll down, and we have our values. We have our value for 5. We were asked for 5, 2, 5, 12, and 16. And so we grab all of those values here in our table, 2, 5, 12, and 16. And that's how I recommend getting all of those different n values, and I'll let you take the time to plug them in on your own notes. So n of 2 equals n of 5 equals n of 12 equals and n of 16 equals, and just see your calculator for these. Now, in part C, we're asked, using this model, can we say whether all 2,800 people will ever be affected? And I did go ahead and give you the graph here so you can kind of see what's happening. And right here at the top, we have a horizontal asymptote at 2,800. And we know, given what we know about horizontal asymptotes, that they only ever approach that line. They don't actually ever cross it. So will all 2,800 people ever be infected? No. The line approaches 2,800 without crossing. And that's because we know 2,800 is our horizontal asymptote. So it never quite infects everybody with these kinds of equations. It just approaches that upper number. And all logistic equations look like this kind of long S value, where it levels off at some value. That's what we call our limiting value at the top. I believe this is one of your homework questions as well, which is why we're talking about it here now, so that you can have a better chance at seeing what it looks like on your homework. All right, so now we have what we call exponential decay functions. See, instead of a population increasing, we're actually going to watch things decay over time. So all that changes about our PERT equation is that we put a negative in front of our R value. We still are going to call P0 our initial amount. P of T is the amount of the substance left. T is our time, and R is our decay rate. And a lot of times our decay rate is really going to come from the half-life. So the half-life is the amount of time it takes for a substance to decay to half its original amount. And that is what is going to provide our decay rate. So whereas before we had a growth equation over here, now we have a decay equation, and you'll see it approach all the way down to 0 over time. Now, we actually have the same relationship between a decay rate and our half-life, the exact same equation as before, and it's just because the kind of negatives that will come out from it being a decay rate instead of a half-life all end up being the same exact relationship as what we have before. Therefore, we still have that R times T, where R is our decay rate and T is our half-life, equals natural log of 2. And so we can solve for R, or we can solve for T. And it's going to feel a little weird, but it is exactly the same as our doubling time. So here's the type of question you'll be asked. This is talking about carbon dating. See, we have a radioactive element, carbon-14, that has a half-life of 5,750 years. The percentage of carbon-14 present in the remains of organic matter can be used to determine the age of that organic matter. So actually using the half-life and measuring the amount of carbon left is how people date things going back in time. So for this example, archaeologists have discovered that a linen wrapping from one of the Dead Sea Scrolls had lost about 22.3% of its carbon-14 at the time it was found. We're actually going to be able to use this information to determine how old the linen wrapping is. And this is a very realistic thing of what scientists do in order to date things. So the important facts here are that the half-life is 5750 and that there is 22.3% of carbon loss, meaning that there's 77.7% remaining. We're going to say, well, how old is the scroll? So first off, let's use that half-life and find our rate R. So R is, of course, ln of 2 divided by 5750. So we're going to start there, and we'll go to our calculator and find that first. So ln of 2 divided by 5750. Now, this comes out as 1.205 e negative 4. So let's write that down, and you'll see how we want to handle this. There we go, back to the slides. This said 1.2 e negative 4. And what that means is you're going to want to move your decimal point 4 places to the left. So 1.2 e negative 4, we move to the left. 1, 2, 3, 4. That, of course, is then 0.12312. 0.00012. So that's our calculator's way of representing super tiny numbers, and all it means is move your decimal place. So we took our decimal place between the 1 and the 2, we moved it left 4 places, and we get 3 zeros. And that is our rate. See, the half-life is huge. It's 5,750 years, which means our decay rate is going to be really, really small. It takes a long time for this item to actually decay. So now let's use that in our formula and see how old the scroll is. We're going to solve for time now. So we don't know what our P0 is, but we do know at this time that we're solving for, we have 77% of P0. So that's 0.777 P0 is equal to P0 e to the negative 0.00012 t. Again, I don't know the initial population, but that's okay. All I know is that it was 77% of the initial population, which I can represent as 0.777 times P0. But then, of course, my P0s cancel once I divide by P0. And I get 0.777 equals e to the negative 0.00012 t. Now my t is in my exponent, so of course I need to take a natural log. I'm looking at natural log 0.777 equals natural log of e to the negative 0.00012 t. And the natural log of e cancels away, so we just have negative 0.00012 t. Then, of course, I have a number times t, so I just divide by that number. I get t equals ln 0.777 divided by negative 0.00012, which we want to go to our calculator now. We go to our calculator, there it is, and we type in ln 0.777 divided by negative 0.12312, enter, 2102.6. 2102.6. So back to the slides. T equals 2102.6. How old this scroll is, essentially. 2,102 years old. So that's how scientists actually date things to know how old something is. I think it's a really cool application of this equation. Now we're going to look at a different example of this decay rate type function. So here we're looking at Newton's law of cooling. If a body of temp T1 is placed in surroundings of temp T0, then the body will cool to temperature T given by this function here, T0 plus T1 minus T0 e to the minus RT. So given a metal pan with temperature 155 that's placed in a freezer of 0 degrees, then after 10 minutes we know that the temperature of the pan is 69 degrees. We're going to use this law of cooling to determine the pan's temperature after 20 minutes. As a quick aside, this is also the equation that coroners use to determine time of death for a given body. They measure, assuming that the standard body temperature is 98.6, they measure the temperature of your atmosphere. They can actually use this equation to determine how long a body has been sitting there. This is a very classic application of this. We toned down the example by just calling it a metal pan for today's example. So we're looking at a freezer being T0 at 0 degrees Fahrenheit, a metal pan at T1 being 155 degrees Fahrenheit, and at T equals 10 minutes, the temperature of the pan has gone down to 69 degrees. How long is it going to be at 20 minutes? So let's fill out what we know so far. We have T0 is 0, T1 is 155. That means our equation, T of T becomes 0 plus 155 minus 0 e to the minus RT. And of course, we want to solve for that R value first using the bit of information we're given that at T equals 10 minutes, the temperature of the pan is 69 degrees. So we have that 69 equals 155 e to the minus R times 10. Right? We plugged in T equals 10 and that the temperature is 69 degrees. And so this will help us solve for our rate. Now the only variable in this equation is our rate R. So we divide the 155 over. We're looking at 69 over 155 equals e to the minus 10R. Then, of course, we take the natural log of both sides. We're looking at ln 69 over 155 equals negative 10R. Since, again, the natural log and the e cancel each other out. And so we now just divide by -10, and we get that ln 69 over 155 divided by -10 is equal to our rate r. Let's jump to the calculator, give this a try. So here we have ln 69 divided by 155, close parentheses, divided by -10, and we get 0.0809. Back to the slides. R equals 0.0809. That's our R value. So now if we want to find the temperature at 20 minutes, well, we have our full function. We know that our function T of T is 155 e to the minus 0.0809 T. So T of 20 is 155 e to the minus 0.809 times 20. Let's see what that value is. We do 155 e to the negative 0.0809 times 20. 30.74. So we have 30.74 degrees Fahrenheit. So after 20 minutes, the pan has dropped down to 30 degrees. So really nice application of this type of decay rate, but it isn't exactly given as a decay rate here. Now we're going to look at some exponential curve fitting. So we might be given several points and told that those points line up to a certain exponential curve. And so we want to actually use our calculator to see if we can solve for those values. We could also be given a logarithmic curve or a logistic curve as well. We also like to curve fit to those as well. So for our first example, though, we're going to see it all fitted to an exponential function. So we're given this chart, which is really a bunch of points. And we say, oh, well, health costs have increased exponentially over the past few decades. It's quite relatable, especially nowadays. So the following lists the national health expenditures selected in years from 1960 to 2012. So we're given a bunch of years, which are our X values, and really X is going to be the number of years since 1960. And we're given our Y column, which is the national health expenditures in billions of dollars. We have all those Y values. So we're actually going to, in part A, use a graphing calculator to fit an exponential function to the data. And I have all the steps for our calculator written down. So going to the calculator now, what we're going to do is enter all of our values into our calculator. And all I did there was stat, and I hit enter under edit. Now I'm going to enter all of my X values under L1. And I'm going to enter my Y values under L2. What's next? 724 is next. 1400, 2600, 2800. And we're told this is an exponential relationship. I could believe it. Our Y values grow much, much quicker than our X values. But let's actually solve for it. So we have all these in our table. Now we can clear it away. That graph was old. Don't worry about that. Now we cleared it away. Now we actually want to calculate our exponential function. And before we do that, I want you to check on your calculator. When you go to mode, go down to stat diagnostics. Down to stat diagnostics. And we got to switch it to on. That way you'll see an R value that's your correlation coefficient. That needs to come up as well. So that's turned to on. And now I can go to stat and I go calculate, and I scroll down and they have an exponential REG, which I can't remember off the top of my head what that stands for. So exponential REG is going to solve for the exponential type of function that we're looking for. I hit enter, and it says, oh, which list are we talking about? And I say, oh, we're talking about L1 and L2. So those are correct. I like both of those. We don't need to worry about frequency. Now we're going to store our regular equation. Yeah, I think REG is just regular equation. We want to store it actually in our y values. We actually want to store it in y1. So we go to vars and we go over y vars, and I hit enter under function. I hit enter under y1. So it says, oh, I'm going to store the output of this function in our y1 position, which is right under our y equals button. So it kind of just puts it in there for us automatically. So I hit enter, and I hit enter under calculate, and you'll see it gave us an equation of the form a times b to the x. And that says, oh, it's an exponential function where it's 34 times 1.09 raised to the x. And these r values here are different than our growth rate or anything like that. This r value tells us how close our points are to actually seeing that curve. So when we look at the points and how closely they actually follow to the line, this says, oh, it's going to correlate really well because that r value is really, really close to 1. So we can't see anything on our graph yet because we need to set our window. Let's set it from 0 to 60, maybe counting by 5, and then 0 to 3,000, counting by 500. And when we look at that, now we can see our exponential curve. So that's what we were looking for. We are actually able to graph a curve that's very close to our points. So now all of those steps are written down here in these slides. Again, just make sure that your stat diagnostics is on, and we saw it in the viewing window. Now in that next part, we're actually asked to graph the function with the scatter plot data. So I actually want to be able to see all of those points, and our calculator can do that as well. All we have to do is turn plot 1 to on. So when I go back to the calculator and I go to our stat plot, which is actually right above the y equals, it's in blue. So I click stat plot and I go under plot 1, I'm going to turn it to on. Now when I go back to the graph, you can actually see the points being plotted, and you can see how well they really fit to that exponential curve. Now, of course, part C asks for a few different values, so we just go to our table and it'll tell us the different values we were looking for the different years. And you can just scroll there to pick all those up. So that's what part C asked for. It asked for the value in 1985, 2003, 2001, and 2016. And our starting year was 1960. So 1985 is 25 years from 1960. So I will let you guys plug those in. And as always, reach out if you have any questions and let me know how these are going. I know it's challenging because there are a lot of word problems. There's going to be 1 or 2 of these on the exam. So please check the practice final to see kind of which problems you should really focus in on, and let me know if you have any questions.